We're going to finish up lecture 12. We'll get through all of lecture 13. Maybe we'll get into a little bit of 14, but it just depends. Either way, we'll get through all the material by Thursday. And we won't really have to rush because there's only about 20-something slides in the next two lectures, and there's 12 in the last. The remaining lectures are actually pretty short. The other thing is we have the second review session for the remaining content that we're covering since the last review session. I put in the request, it's likely going to be approved to be in the same room as it has been, which is 106 Scott Hall. It'll be on Thursday at 5 o'clock. Okay, but perhaps Friday might be a bit too late because people are heading out early to go on break. So Thursday at 5 o'clock, likely in 106 Scott Hall, is when the second review session will be to cover the rest of the respiratory material. I will send out an email as soon as I get confirmation from the scheduling office that it actually is going to be there. All right. Yes. We covered 9 through 11 last time, right? So we should all cover it. Yeah, it'll cover everything else. There's not the lecture 15 is the high altitude phys. And there's some good stuff in there, but we're actually going to touch on a little bit of that content here, so that there's not a lot of new content. All right, let's get started. Okay, so the last thing we left off on was we were talking about recruitment versus distension. This has more to do specifically with the types of airways and the types of blood vessels that are going to be used. We have the two terms are both going to contribute to an increase in the ability to ventilate and perfuse and have increased gas exchange, but it's going to really depend on the difference in the definitions. Recruitment means that you're going to pull together more of the vessels, more of the alveoli are going to be able to be thoroughly inflated, but more vessels are going to be able to perfuse and participate in gas exchange. Distension is any of these vessels that are going to extend and expand. So an example here is we're looking at some of our blood vessels to increase perfusion. You have the blue is showing that some of those vessels are collapsed. Remember we talked about critical closing pressure when we were in microcirculation? You need a certain amount of driving pressure in order to maintain open capillary beds. This is actually going to be a good thing when it comes to maintaining normal ratios of ventilation and perfusion, as well as making sure that your blood can be diverted to the proper parts of the body. So on the left side, we're looking really at the scenario here, like at the starting point, where you have some blood is flowing through these capillary beds. Some are open, and the ones that are blue are actually closed to blood flow. Recruitment is what's happening here, where you are actually recruiting more blood vessels so that they're going to pass blood through neighboring alveoli in order to increase the number of blood cells that are participating in gas exchange. Distension is what's happening over here. Distension is going to be necessary to expand and increase the overall flow per blood vessel. Okay. The reason that we want to make sure that we're looking at both of these patterns is that you could have a relatively minor amount of blood flow that can reach capacity long before it comes anywhere close to being a third of the way from that contact point between the capillary bed and the alveoli. If you distend it, you're going to get a greater degree of blood flow, and you're going to move the blood faster through there, which means you're going to have gas exchange occur at a higher rate. So both of these together are going to improve the perfusion side of things to make sure that all the alveoli that are being ventilated are going to be perfused so that they can contribute gas to the body. Now, our VQ ratio. V is your ventilation, Q is your perfusion. What do you notice about the pattern between blood flow and ventilation from the base of the lungs to the apex? Which way are they going individually, the dashed lines? Down. Both of them are decreasing, okay? Blood flow is a lot higher at the base of the lungs. Remember, about a quarter of all of your cardiac output is actually sent down to the base of the lungs. it decreases substantially by the time you get to the top of the lung. It's this variation and this non-uniformity in ventilation and perfusion throughout the lungs that is the result of different VQ ratios you can find based on spatial location. Okay, your ventilation is also going to be higher at the bottom, and it will decrease as you get to the top. That might seem counterintuitive considering we talked about the top being more well ventilated because of the more negative interpleural pressure. That is true. But as a general rule, more of the air as you are going through the respiratory cycle is coming into the base of your lungs. When we say that the upper part, the apex, is more well ventilated, it's mostly referring to at your functional residual capacity. More air remains inside the upper part of your lungs at the apex than does at the base. But they do cross over. So the blue line is actually showing the ratio of ventilation to perfusion. So at the base of your lung, you have a relatively low VQ ratio. Why is it low? Which one of those parameters is higher? Which one? Q, the blood flow, right? So if the denominator is bigger, then the whole ratio is going to be lower. At the top, you have more ventilation than you do perfusion. So the relative ratio is going to be a little bit higher, right? Higher numerator, denominator is a little bit lower, you're going to have a higher VQ ratio. The VQ mismatch is going to come into play when we start to have pathological conditions. But the actual ratio itself is going to change based on the region of the lungs. So if we were to look at the relative amounts of we're doing the PO2 in the alveoli on the x-axis, and we have the PCO2 in the alveoli on the y-axis. Okay, so this is really going to compare what is happening in the ratio between the amount of CO2 and the amount of oxygen that is present as dissolved gas. Okay, remember, your partial pressure is going to be dissolved gas. That's going to come into play in just a little bit. What do you notice about the inadequate ventilation portion up here on the top left? The VQ ratio is what? It's 0. What would that mean? Something that has a VQ ratio of 0. It's not ventilated, right? If the ratio is 0, then the numerator is 0. Okay? So this is an area that is not ventilated. These are an alveoli and blood vessels that are in communication with each other. There's the potential for gas exchange, but none is occurring because there is no fresh air coming in. What do you notice about the partial pressures? What do they look like?
That's what you would see in your pulmonary arterial side.
Pulmonary arterial side, yes. I was thinking systemic. Yes, exactly. I was thinking systemic venous, pulmonary arterial. So the amount of gas that you would find feeding into the lungs, okay? This would be similar to what you would find in your systemic venous, that 40 and 45 relative amounts, because that blood is passing directly from the right side of your heart, the systemic venous, to the pulmonary artery, and it's not being ventilated, okay? It's going straight to the left side, which means what is it going to do to your systemic arterial oxygen tension if there's a significant portion of blood that's been shunted? What would you end up with? Some of your blood's being oxygenated, some of it's not. It's going to mix, and what does that mean for your saturation and your oxygen partial pressure going into the arterial side of your system? It's going to be lower. You'll end up with some hypoxic or hypoxemic conditions that are entering into systemic arterial. This is what's called a shunt. It is shunting blood directly from the right side of your heart to the left side of your heart without ventilating. Okay? So that VQ ratio is going to be 0. Your normal value is roughly 100/40. This is what you should see, right? We should have, after we have gas exchange occur, we should have a partial pressure of oxygen somewhere around 100 and a partial pressure of CO2 somewhere around 40. That's typically the values that we're gonna find in your pulmonary venous leading into your systemic arterial circulation. Okay, that's properly ventilated. That VQ ratio is about 0.8. That's considered normal. Okay? Anybody remember why it's 0.8? Our standard human patient. 150 pounds. You will always have 5 liters per minute of perfusion, cardiac output, 4 liters per minute of ventilation. 4 divided by 5. Okay? So your normal VQ ratio is going to have the typical values that you see on your systemic arterial side. What happens if you have inadequate perfusion? Your VQ ratio is now infinity. Why? What's wrong with the perfusion side? Your denominator is, when you divide it, you can by 0. No, so you get infinity. If you don't have perfusion, this would be considered wasted ventilation, right? These alveoli are being ventilated, air is still entering in, but there's no perfusion, which means no gas exchange is occurring for this particular alveolus. As a result, you end up seeing partial pressure of oxygen mimicking the humidified air that you have inside the alveoli that you just breathed in. And since you don't have any CO2 in the atmosphere, it's so negligible for our purposes, it's 0. You're going to see these values for a wasted ventilation. That VQ ratio is going to show up to be an infinity, and the gas in those alveoli is going to remain the same as what was inspired. So whatever you breathed in, you're going to breathe back out. Okay? Any questions so far? These 3 parameters are up here on the top. Point A, point B, point C. All right, so a summary to talk about mismatch. If we don't have the correct normal VQ ratio, that can happen because of disease, it can happen because of some kind of obstruction that's blocking either blood flow or airflow. You can even have that when you have a super bad cold. You can actually have so much congestion that you are blocking air from entering into some of your alveoli. Okay? There are a lot of different examples. What would be one example of something that would cause a shunt? A hole in the septum? Oh, so yes, the shunt by definition is a shortcut. Yes, so it would. So what would be in this example? I'm talking about a pulmonary shunt that shunts blood from the right side to the left side directly. So you could have it directly, completely bypassing the entire circulation system. But specifically, if it entered into the circulatory system and you have a problem in the lungs at the capillary point, what would cause a shunt? How could you have perfusion but no ventilation?
Pulmonary embolism?
So pulmonary embolism would actually be something that would give you ventilation but no perfusion, because the embolism would specifically block the blood flow. It would block off the perfusion of a particular alveolus so that it would be ventilated, but it wouldn't actually get any blood.
Pneumothorax.
That would be an example of something that would be no ventilation, but you could still be perfused. Any kind of atelectasis, which is just collapsing of an alveoli, a pneumothorax is kind of a big reason for that. But it could be something as small as inhaling something that gets caught and obstructs it. So if you aspirate something into your lungs, which does tend to happen, especially as you get older, people's irritant reflexes and coughing reflexes tend to diminish a little bit, and so you might not be able to cough something up as well. You can get something lodged and it will actually block the ventilation. Perfusion will still occur, but ventilation will go away. And both of these situations are going to result in a mismatch, which means you are going to have some alveoli that are being ventilated, but it's basically useless ventilation. Or you could have some blood that is passing across alveoli that really serve no function. Okay, so your body does have ways to adapt to these issues so that you can try to repair and get these VQ mismatches back into the normal ratio. So, first example, I have 3 that I want you to run through really quickly just to see if we're all on the same page. In this example, we have an alveolus, which is my hexagon. On the bottom is your blood flow. That is the gas pressures coming in on the capillary side. And that little blue square, or rectangle, I guess, it's not exactly even, is an obstruction of air entering into that alveolus. So what would you expect to see in the red box? What would you expect for your gas pressures in this example where you have perfusion and no ventilation? And what do you expect your VQ to be? So, because this is a word answer, none of you will have it show up as being correct, because I'm sure you will type exactly the way that I did. But, when we're looking at unventilated alveolus, what's the end result? Same exact gaseous partial pressures that you would find on your systemic venous side. Your VQ ratio is going to be 0 because the numerator is 0. Whatever your perfusion is, doesn't really matter because you're getting absolutely no ventilation. All right, next question. What's considered normal? Inspired air. You are putting the correct value. So, for these ones, what do we see? Oxygen should be around what? For normal. How many milliliters per mercury? Why you got it right? 100, right? And your carbon dioxide? 40, right? Normal ratio, we have our normal gas exchange occurring. Oh, there we go. Oops. You should have 140 because this is the situation that we would normally find. This is what we want to find, where you have normal gas exchange occurring, and you end up with switching from your systemic venous partial pressures that we have after you pass through the tissues, after everything's been oxygenated, heading into your arterial side. All right, next up is the last one. What happens if you have some kind of blockage on the perfusion side? What would you see in that blue box? And what would your VQ ratio be? the value should be the same as whatever you've inspired that you've already humidified. Okay, so not the partial pressure of the air that you're breathing in that's dry air, you've humidified it, so it's got to be a little bit lower than the 160 that you'd be breathing in. So you're looking at the same partial pressure for oxygen and carbon dioxide that you breathed in, and your VQ ratio is going to be infinity. Why? No Q. Okay? This is not just something that would happen if you had a pulmonary embolism. An embolism can be anything that blocks flow. You can have an aeroembolism, you can have a blood clot that would cause an embolism. You also could have another situation where, let's say you had a tumor, unfortunately, that was pushing in on some of these vessels. That can also restrict blood flow. Okay, there are a lot of different things that can happen that can cause blood flow to be cut off from interaction with alveoli that actually has nothing to do specifically with blood clots. Okay? Pulmonary embolism, a blood clot in your blood vessels is usually the simplest example that most people get. All right, how do we feel about VQ ratios and these three parameters? Okay. Next up, this is my little summary chart that just says everything that you just did. All right, so what happens? It's a little slow. What happens if you have ventilation of an alveolus that is not perfused? So the problem is some kind of blockage. That is happening here. There's some kind of blockage, but you still have air that is going in to both sides. Okay, so the ventilation is not the issue. Air is going into both lungs, not a problem. These figures are going to show you something that's affecting an entire half of the lung. That's not very realistic, but for simplicity's sake, let's pretend that each side of the lung is going to function as an individual unit. What do you see as the difference between these two pressures here? Between the unperfused and the perfused. The unperfused has what? What is that similar to? Those gases on the right. The air that you breathe, right? The air that you breathe in from the atmosphere that's been humidified. What's happening on the left side? The problem is you are going to have a little bit lower oxygen and a little bit higher CO2, mainly because your blood that should be going to the left lung here is actually causing the right lung to be hyperperfused. The blood that's coming out of the right side is still coming out at the same cardiac output as the left side of the heart. So if it can't go through those vessels, it's going to be diverted to the other part, which means you're going to have a higher perfusion of the well-ventilated, healthy lung that is actually able to participate in gas exchange. Okay, so all these are really saying is that you're going to end up with a decrease in the VQ ratio because you are hyperperfusing. So perfusion on your healthy interaction is going to go down because the blood that should have gone through the blockage now can't. So this is what's going to happen under normal circumstances without any kind of compensation. So you're going to have a pretty big discrepancy between your left and right side. On your side of the blockage, which is your left, because we're looking at a person, this is the left side, you have a VQ ratio of infinity. You have a lower than normal VQ ratio on the right side due to hyperperfusion. What do you think would be a response the body could do in order to try and restore normal VQ ratios in the lungs?
Does the pores of cones have something to do with that? Where the air, so if the left side of the lung has pulmonary embolism, one has some kind of blockage, then that air is not going to be able to move into the left side. So then that means that hypoventilated side of the lung will take that air and move it to the right side of the lung. So the right side will be hyperventilated. So in order to get that air back over to the left side, would it have to do something with the pores of cones to move that air?
So it wouldn't actually have to do with the pore of cone. That is a connection between neighboring alveoli to make sure that the neighboring alveoli don't collapse, and it kind of helps them to stay inflated. But you are on the right track.
perhaps shrink the unperfused lung so that the one that's normal can expand into that space?
Yes, it does accomplish the same thing, where you are reducing the amount of air that is going into the lung that is not being perfused. So in this case, how would you do that? You would constrict, sorry about this, constrict those bronchioles. So, text there. By constricting those bronchioles, you're going to divert the air that's being taken in a normal tidal volume to the healthy lung that is actually being perfused. So, and how is that going to happen? You are going to really sense, the vascular smooth muscle cells can sense the drop in the pH, the elevated PCO2 or the low PO2 that resides in the surrounding area. But in this case, we're looking at well ventilated but not perfused. So this is when we talk about vascular smooth muscle cells being able to sense changes in pH. Usually we're talking about acidosis because it's inadequate oxygenation. In this case, we have very good ventilation but no gas exchange. So the perfusion is the issue. So this is going to result in constriction of your airways, right? When you have sympathetic stimulation and you do have that drop in pH because you are exercising a lot or you're running away from the tiger or whatever it is that you're doing that causes sympathetic stimulation, what do your airways normally do in response to that because you have low pH, high PCO2? They dilate. So if your PO2 is high, your PCO2 is low, your pH is a little higher, the opposite is going to happen. This can happen not just in an entire lung, it can happen on individual airways. So that anything that is distal to that blockage is not going to receive as much air. So it can selectively constrict bronchioles that are leading to the alveoli that are not being perfused. And that would be one of your compensatory mechanisms in order to try and reestablish that ventilation-perfusion ratio. Problem is perfusion, so you can regulate where ventilation is happening. Send more of your air into the part that's actually being already hyperperfused. That low VQ ratio on the right lung will be restored to normal, and that infinity VQ ratio on the left lung will be brought down toward a more normal value. How do you feel about that?
Would a plaque be able to cause this kind of issue as an obstruction?
Mm-hmm. Yep, not just a blood clot, a plaque, anything that is sufficient enough to cut off blood flow entirely to the capillary that is passing underneath the alveolus.
But it has to be directly in the capillary, it can't be more upstream.
Oh, no, it can definitely be upstream. Anything that's going to cut off flow into that capillary. So any of the capillaries that are downstream from an arterial or, gosh forbid, a larger artery would be subject to this kind of non-perfusion of that part of the lung safety. All right, so ventilation of unperfused alveoli. Now we'll do perfusion of unventilated alveoli. So let's say that you inhale something and it blocks out all airflow to one side of your lungs. That's the example that's shown here. Now we have a situation where your VQ ratio in your healthy lung is much higher. Why? Because it is going to be hyperventilated. You're still taking in the same tidal volume, it's just that now all of it is going to the one side of the lung that is still functional. Blood flow hasn't really changed all that much at the moment that this happens. There's no compensation in this scenario. So, number one says that your ventilation is stopping in that one lung, which means what's going to happen to your VQ ratio? It drops down to 0. No ventilation, normal perfusion. If the numerator is 0, it doesn't really matter what your perfusion is, your VQ ratio is nothing. The gas is going to be the same as what is coming into it from your systemic venous, which means this is considered what? Dead space or shunt? Shunt, okay? Dead space is your wasted ventilation. It's ventilation of alveoli that don't participate in gas exchange. That's part of your alveolar dead space, which that contributes to your physiological dead space, which we calculate by which method? Fowler or Bohr? Bohr, right? Because Bohr uses CO2. So just recap from earlier. Well, from last week, earlier in this lecture. So, in this circumstance, we end up with a higher VQ ratio because all of the air is being diverted to the healthy lung. But that lung, while perfectly fine being perfused, gas exchange occurs, you now have whatever blood is passing through that unventilated lung is going to contribute venous blood gases to your systemic arterial side, which means what in terms of your overall partial pressure of oxygen going into systemic arterial circulation?
Decrease.
It's going to decrease. You're going to end up becoming a little bit hypoxemic. The degree of that blockage and the remaining perfusion of unventilated alveoli will determine how severely hypoxemic you are. And if you're hypoxemic, meaning low oxygen in your blood, your tissues will become hypoxic because of low oxygen in the tissues. So, how are we going to respond to this? What would you do if you have a relatively low oxygen and a high CO2? What would your vascular smooth muscle cells do?
Relax.
Or,
The one block open and
sorry, on the blood side. The vascular smooth muscle cells around your blood vessels. Right, because this is, all of the air is going to go into the alveolus, into the well-ventilated lung. So the compensatory mechanism here is trying to compensate for the blood going somewhere that it can't ever have any gas exchange. Because in this case, I said if you breathe something in, let's pretend it's something more permanent. You have a mass that is actually compressing on those bronchioles. So anything downstream of that can't get any because this physical mass is compressing it and blocking any airflow. That's not something that you can control by changing the diameter of your airways. The only thing you can change in order to restore these ratios to normal is controlling your blood vessels. So what do you want to do in this circumstance? Where do you want blood to go? To the healthy one, right? The problem is that on this side here, we have perfusion and no ventilation. We have lots of ventilation and normal perfusion. So we actually have a relatively high VQ ratio because it's overly inflated due to normal tidal volume. You have more of it going into one lung when it should be split going into two lungs. So what would you do in order to fix that? Where do you send the blood? To the healthy lung, and how do you do that? You constrict the blood vessels going to the blocked lung. Okay? Because the tissues are hypoxic, right? There's no fresh air coming in. So the tissue around in there, the blood gases around there are more hypoxic than you would find normally because there's no gas exchange occurring. You get this vasoconstriction occurring on that side because the vascular smooth muscle cells will respond to that hypoxic condition.
Is the compensation vasoconstriction on the unhealthy side rather than vasodilation on the healthy side because of the change in pH?
Because of the change in pH.
Okay.
The other thing is that we typically what's happening is this also can be contributed to with sympathetic stimulation. It's the same principle that we talked about with circulation. Your sympathetic system innervates your blood vessels, parasympathetic doesn't. So the only thing you really do is either constrict more or constrict a little bit less. In this circumstance, these cells that are directly in contact with extremely hypoxic conditions that they're not supposed to be in contact with because they're on an arterial side as opposed to a venous side, they will respond to an unusual change in that pH. The elevation in pH that you potentially can see on the other side is actually not really going to be that significant. It's a bigger pH change on the other side.
Is the difference between the arterial and the venous, like expected lowering? Like how do you differentiate between normal pH changes induced by like exercise versus this?
Oh, so This would typically be something that would be because of, like a long-term issue. But specifically the drop in pH that's happening here, this shouldn't happen. You should not have low pH even if you're exercising, because what do you do when you start exercising? You breathe faster. And where is all that air going? It's going into your lungs, which means that the area right around your lungs should have a normal physiological pH. Only the respiring tissues, the skeletal muscle, are gonna have that big drop in acid. If you are losing that oxygen and getting rid of that CO2 and you're not able to blow off that CO2 like normal, this area should always have a relatively physiologically normal pH. So any change that drops below that would cause that reflexivity.
So if you were choking, it could cause like a pulmonary hypertension where because all those blood vessels start squeezing down, because there would be very hypoxic conditions.
Yeah, well, so it would still be, that response takes a little bit of time because you have to wait long enough to get that pH change to have that reflexive vasoconstriction. If you are choking, you probably pass out from lack of blood flow before any of these kinds of changes to compensate for that would happen. But in this example, it's choking on something, having it go in and block one of the lower ones. If it gets past those irritant receptors, then this is where something like that would come into play. Any other questions? Okay. That's it for this one. Now we can go into our regulation. All right, so how do you regulate your breathing? I'm going to get into nerves, right? Excitatory and inhibitory nerves. Different regions of your medulla and your pons, so a little bit more of the neuro side of things. All right, so what do we need to do? You have an automatic rhythm. You have what's called a central pattern generator that generates your normal breathing pattern. And you have the ability to modulate that based on what you're doing at that time. If you are more active or less active, if you're sitting, standing, crunched into a ball, all of those are going to change your breathing rate. If you're sitting, if you're talking for 75 minutes, my breathing rate is different than your breathing rate. Okay? All of these things are going to happen. Same thing if you are eating. You don't want to be breathing and eating at the same time. If you couldn't regulate that in response to changes in activity, we'd all be choking all the time. So, this is from the Boren book, and it gives you a lovely little pattern to show you what is actually occurring. So I already mentioned here we had our central pattern generator. This is the group of neurons that are in the medulla that are responsible for generating eupneic breathing. So E-U-P-N-E-A. Eupnea is normal breathing. Anytime we talk about tachypnea, dyspnea, that all is in reference to your normal rate of breathing. Okay, eupnea is just normal breathing pattern. Your central pattern generator are present in your brainstem, the lower part of your medulla, and those neurons are responsible for sending the excitatory signals to innervate your phrenic nerve to start regulation of inspiratory signals. That will go down through the spinal cord to those muscles in the system, and you will have different ways of sensing what's happening to your breathing rate. You'll have stretch receptors in the lungs that will sense when air is inflated, and they will feed back to stop you from breathing. That doesn't really happen so much in adults as it does in infants. I'm going to get to that in just a second. As you increase your ventilation, you can see changes that are going to happen in your chemoreceptors. We are going to talk about the chemoreceptors coming up in just a little bit. Those peripheral chemoreceptors are sensing blood gases that are going to the body. Okay? You have, just like with the baroreceptors, you have two sets of peripheral chemoreceptors. One that's going to sense blood going to your brain, one that's going to sense blood going everywhere else. Sensory integration is also going to happen inside of your brainstem. And that is also the location in the medulla where your central chemoreceptors are. Your central chemoreceptors are really responsible for sensing most of your change in pH and change in CO2. Your peripheral chemoreceptors can sense a little bit of that as well, but they sense changes in oxygen. So that's going to come into play when we start talking about high altitude physiology. Okay? All of those can feed back onto your central pattern generator in order to regulate the rate at which you're breathing. You do have some voluntary control coming up from the cortex. So there are two main pathways. You have a corticospinal pathway, which is the one coming from the cortical region that allows you to consciously decide when you're going to breathe or when you're going to hold your breath. Then you have a bulbospinal pathway that is a descending one. That's the automatic signal that originates in the brainstem. So two different spinal tracks that these nerves will travel down in order to control your breathing rate. Okay? Can you hold your breath indefinitely until you die? No, you can't. You physically can't. Your body will get mad at you and it will force you to breathe. Okay? That is directly responsible are those chemoreceptors. You can try to hold your breath as long as you want. But eventually, your pH is going to drop, your CO2 is going to be too high, and your medulla is going to force you to take a breath. Okay? Your body wants you to survive, your brain wants you to survive, and if you decide to hold your breath, you're not going to be able to at some point. That's a big problem if you're underwater. Okay? So, this is the main pathway that we're going to talk about for regulation of ventilation. How are we going to regulate the rate at which you're breathing? Okay, this is a lovely simplified version that shows you that you can have your excitatory input. A lot of it's going to come from the medulla. The DRG, for those of you that did any neuroscience class, this DRG is not dorsal root ganglion. This DRG, in the context of what we're talking about, is dorsal respiratory group, okay? And then we'll talk about VRG, which is ventral respiratory group. It's a group of neurons that are going to control the rate at which you're breathing and whether you're doing inspiration or expiration. So inspiratory neurons are present as part of your dorsal respiratory group. They are going to help dictate whether you're breathing in and how rapidly. By sending signals down into the spinal column around C3 to C6 is where your phrenic nerve will start to leave from the spinal cord. You have two. They innervate each half of your diaphragm. So if one of them is damaged, you still have another phrenic nerve. It just means that only half of your diaphragm is functional. Okay, so you're not going to get the same force of contraction to lower that intrapleural pressure. You'll get about half that. The phrenic nerve phrenic nerves will innervate your diaphragm. That will stimulate specifically that skeletal muscle to contract. So these are motor neurons, meaning they directly innervate muscle. A premotor neuron is going to be something that is a nerve that innervates a motor neuron, and then an interneuron is just the connecting highway, sort of the middleman. Okay? Starting with our dorsal and ventral respiratory groups. So looking here on the left, again, this is from the Boron book, and we're going to look at inspiratory on the left. The big ones that I want to mention here are that your inspiratory nerves are specifically looking at your, let's see if I can find it on here, your intermediate, ventral, and your DRGs. Okay? So here's your phrenic nerves, and these are the nerves that are responsible for, all of these ones in red are responsible specifically for causing inspiration. You'll have nerves that will innervate your pharynx, your throat, your mouth, everything that's going to help you to draw air in. Okay? This whole area up here is the medulla. All right? In your medulla, point a little bit better to our DRGs. all the lines over here. It's labeled over here. But those are not expiratory nerves. It's just labeled on that side because of all of the nerve fibers that they're drawing on the inspiratory output. Your DRG, your dorsal respiratory group, and some of your ventral intermediate group. Those are all contributing to inspiration, okay? They innervate, as I said, parts of your mouth, your upper respiratory tract, your diaphragm. They're helping you to bring air in. Your ventral respiratory group, so looking specifically at the rostral and the caudal VRG. So that is looking at anything over here in green. That's expiratory output. Now, what kind of expiration are we talking about? Active, right? Passive just involves relaxing your inspiratory muscles. Under normal tidal volume, normal quiet breathing, your caudal and rostral ventral respiratory group neurons are quiet. You're not forcing any air out, so you don't need these nerves to be firing. All you need to do is relax the inspiratory output. Okay, so for inspiration, we're looking at dorsal respiratory group and then the intermediate ventral. So some of the intermediate fibers. For your expiratory, the bulk of it is your rostral and your caudal. The rostral is really responsible for being the interneurons I mentioned that will feed into the caudal, which are your premotor and motor neurons. Basically, because you're starting from higher up in the brainstem and you're moving down toward where the nerves will be sending out those inputs to those intercostal and abdominal muscles to force air out. How do you feel like this? For those of you that didn't do 503, I know this might look a little confusing. We do a lot of nerve stuff in the fall semester, but the takeaway here is you should know which neurons are responsible for breathing in, which ones are responsible for breathing out, and that your expiratory ones are not quiet expiration. They are for forced expiration.
Does this diagram include, I know we mentioned about expanding the rib cage, and so there were muscles that control like the back as well as like opening up parts of the things that just
Sternocleidomastoid, yep, and your scales,
And
yes.
Is that on there anywhere?
Yeah, so it's other muscles.
Oh.
That would be over here, all of these. So this is showing all the stuff, the muscles from the upper part, and then the larynx and the pharynx, and then this one is showing your other muscles that are going to help you bring in. And you also have the spinal nerves that are going to innervate the intercostal muscles as well as your those ones that we mentioned that will help you lift the rib cage. So all of these are responsible for inspiration. The ones that I circled in red are your expiration, forced expiration. All right, so one other part I want to talk about here is, this is really, let me see if I can zoom in a little bit. The text is a little small, and I tried to enlarge it, but then we figured it would on the screen. So starting up here, we're going to look at the pons, which is sort of that bolus area, and then the medulla is right below it. Zooming in on that, we have a few key points. We have our ventral respiratory group that we've already discussed, and we have our dorsal respiratory group. They're just called dorsal and ventral based on where they're present in the body. So dorsal would technically be closer to your back, ventral will be closer to the front of your neck for the brainstem. And then next up, we're going to talk about the apneustic and pneumotaxic centers. The big takeaway here, you see the plus and the minus. Apneustic is going to control inspiration. It will stimulate prolonged inspiration if allowed to go unchecked. The pneumotaxic will help to inhibit that inspiration and slow it down. When we get down toward the bottom, you'll see that these dorsal and ventral respiratory groups are going to stimulate the different muscles that we had talked about before. Diaphragm and external intercostals for breathing in, internal intercostals and accessory muscles for forced expiration. All right, now, our pneumotaxic and our apneutic. Our apneutic center was discovered experimentally. It was found that if you did a section, like a lesion, and you separated right above the apneutic center, between the apneutic and the pneumotaxic, and you did a bilateral vagotomy. Just like with your phrenic nerve, you have two vagus nerves. Okay, one for the right, one for the left. If you cut both of those, and you take the apneutic center and you cut in between these two, oops. So if you cut here, and you cut both vagus, you end up with prolonged inspiration. Basically, the animal can't shut off breathing in. So they start breathing in and they just continue to breathe. The pneumotaxic center, one of its functions is to kind of help inhibit that. It's not absolutely essential for normal breathing because as long as your vagus are still intact and your apneutic center is intact, if your pneumotaxic is not functioning normally, you can still shut off inspiration by way of the vagus. But it's sort of an extra fail-safe that if something happens to your vagus, the pneumotaxic can send inhibitory interneurons to that apneutic center and allow it to shut off inspiration, stop inspiration so that everything can relax and you can start breathing that air out. Apneusis just means prolonged inspiration. So there's a figure coming up, I believe next, yes, that will show you what apneusis is. So that's right here. On the third one down shows you that prolonged inspiration, okay? Eupnea, as I said at the top, that's just your normal breathing. A sigh would be something that would be triggered when your blood gases are, you're ventilating at an inadequate rate to be able to counteract the blood gases. Sometimes you'll take in a deeper breath to try and get more oxygen in. Do you notice how the vagal breathing and the eupnea are slightly different? You still get that same general pattern, but it's a little bit longer than without the pneumotaxic. And you have vagus being the only one that's shutting off that inspiration. That is something that you will see being a little prolonged. So those are things that we've discovered through experimental design, studying different animals and how different nerves, when they're disrupted, can regulate ventilation. These are not things that you would normally see in a person. On the right, these examples are things that you could see depending on if you have different types of pathologies. This is not something that you need to know specifically, being able to draw all of these. Ataxic breathing, if somebody mentions ataxic, it just means it's really erratic. Cluster breathing means several short breaths and then a long period of apnea. Gasping is one big breath and then a long period of apnea. The Cheyne-Stokes respiration, that's something that actually can occur in people who are sleeping at high altitudes, but it also can occur in normal people who have congestive heart failure. It's just sort of a ramping up of inspiration and then slowing down. And so it kind of goes through cycles. It's usually a pretty benign pathway, but it is something that is usually indicative that there's some other problem. It's not really a respiratory problem, it's a problem that is causing the nerves to fire in such a way that you end up with this Cheyne-Stokes pattern. The experimental animals, that's how we discovered things like the apneutic center. That's how we discovered how important the vagus was in shutting it off. And we're still working on trying to identify what else the pneumotaxic center could be doing besides just being a backup for the vagus. Because nothing in your body is usually there just for redundancy. All right.
A quick question.
Yes.
So agonal breathing, which one of these is that?
Which one?
The gasping, agonal breathing. Like I heard when people are starting to really get close to death, there's something going on and they're
Oh, so yeah, that would indicate that would be more of the gasping breath, and that would, depending on what the cause is, a lot of times that would be because of dysfunction in the nerves themselves. They're either firing erratically or they don't have the normal feedback mechanisms, and so when you get if you're not breathing at a normal rate, you'll have a buildup of CO2, and that will trigger a stronger response to try and compensate for that. But the exact pattern will change based on what the cause is of that irregular breathing pattern.
The Newsis versus the vagal breathing, like is the flat line, just, you just take like a really big inhale and then hold it until the body forces them to exhale, or are they just like continually slowly inhaling?
Oh, no, so you'll still breathe in until you hit capacity. You can't breathe in more air than your lungs can fill. So you will breathe in, and then you just won't be able to relax those muscles to let the air out. So it just kind of stays.
So it's not like a drawn out inhale, it's just like you
No,
inhale to
yeah.
capacity and then hold it.
Yeah,
until
so
body forces you to
the
breathe out.
inspiratory phase. So there are actually like three phases of breathing. You have an inspiratory phase, the switch from inspiratory to expiratory, and then the switch from expiratory to inspiratory. And so when I said it's a prolonged inspiration, it's the phase of breathing, which means you're stuck on the inspiration side and you don't get that signal to shut off breathing in to get that signal to the expiration to begin. All right. So this is going to lead us into our next part where we're going to talk about regulation of breathing in terms of how you get feedback, sensory feedback from the body in order to change the way that you're breathing in response to changing conditions. Our negative feedback. You have some kind of stimulus that is here at the bottom. This stimulus is going to cause something. It's going to be a positive or negative stimulus, and that signal is going to have to be received by something in the body. That receptor will send whatever that signal is to alert you that you have a change in the normal status quo to an integrator, which will collect signals from all over the body. And that will basically take them all and come up with a defined response. That effector is going to signal to whatever tissue, whatever muscles are going to enact that response. And hopefully that will counteract that stimulus to feedback to reduce whatever that change was. So if you have a positive stimulus, everything will work and that response will help to bring that positive stimulus back down to its normal set point. The first example actually has to do with what I mentioned before about stretch receptors. Your lung does have stretch receptors that are really important for infants. They're learning how to breathe for the first time, so how do they know how to regulate when to breathe in, when to breathe out? The stretch receptors that are in the lining of your lungs will respond as the lungs expand, and it will actually result to inhibit further expansion and trigger that switch to expiration, okay? It's mediated by the vagus, and basically all it does is it prevents your lungs from overinflating. You don't really see that in adults unless you are at very high lung volumes at very intense exercise. Then you might see a little bit of this Hering-Brewer reflex kind of kick in. It's much more noticeable in infants as they are first learning to breathe air instead of amniotic fluid filling up their lungs. Okay? And all you're really seeing here on the bottom is when the red line shows inflation of lung volume on the top, you see a ramping up of vagal activity and a ramping up of the phrenic efferent activity. So afferent, for those of you that didn't do 503 yet, means it's a sensory signal going to your central nervous system. Efferent is exiting the central nervous system. So afferent is sensory coming in, efferent is motor coming out. So the vagal signal is telling you that stretch receptors triggered, they send a message to the vagus, it communicated to the central nervous system that the lungs have inflated. When that gets to a certain point, it will actually signal the phrenic nerve to shut down. And as you start to reduce your lung volume, you see the sensory will have a reduced signal of that stretching, and the phrenic efferent activity is also going to be depressed. Okay? If you have no inflation, then that's, your vagus isn't really sending any kind of sensory signals. All right, so this is our little flow chart, really just showing that you can have some influences from your higher centers, but your central pattern generator, the centers, the respiratory control center that is inside your medulla, is really going to be responsible for sending all of those nerves that we already talked about with the dorsal and the intermediate ventral respiratory group
to control the muscles for breathing. You will have some reflexes from peripheral chemoreceptors and central chemoreceptors, and you'll have other reflexes that have to do with stretch or irritation, changes in temperature, any kind of changes in pH. All of these are going to signal to that respiratory control center to ramp up or depress your breathing rate. This one I can't remember if it comes from Geithner or if it comes from Bernard-Levy, but we're going to spend a lot of time talking about these chemoreceptors. We've already talked about our stretch receptors. But the other one I wanted to mention is our irritant receptors. Your lungs should be free of all debris, free of any kind of irritating solid object or some kind of gas. Has anybody ever had the misfortune to be around pepper spray? Even if you just tested it to see if it worked, okay? What happens? You gag, you cough. Or if you've seen a television show ever in your life, pretty much you've seen somebody responding to pepper spray. Those irritant receptors are basically the sensing of the capsaicin for your pepper spray example. And what it does is it causes severe bronchoconstriction. Why? It's trying to stop that irritant from getting down into the alveoli, where it can damage those very thin layers that are necessary for gas exchange. So what they do is they will actually inhibit the medullary respiratory center. Why? They don't want you to breathe in anymore. The goal is to stop all inspiration and cause coughing in order to get anything out. So when we're looking at the peripheral chemoreceptors, the central chemoreceptors, receptors that are present in your muscles and your joints, all of these are going to stimulate the respiratory center to increase breathing in response to changes in blood gas or changes in activity. Your stretch receptors and your irritant receptors, when they're firing, they inhibit. Because the goal is, if you're stretching, that signal says you already have enough air, let's inhibit this and stop inspiration. Same thing for your irritant receptors, okay? And you get a reflexive, not just a coughing mechanism, not just a shutdown of your inspiration, but also a reflexive constriction of your airways to prevent anything that was present there from being able to move further down toward the alveoli. All right, so now let's get to the fun part. Our chemoreceptors. On the left side, we have our central, on the right, we have our peripheral. The central chemoreceptors are going to be located in the medulla in your brainstem. They will sense elevations in CO2 partial pressure and a drop in pH. They do not sense oxygen at all. The only way they know that you don't have enough oxygen is because they sense CO2 and pH. Your peripheral, your aortic arch and your carotid sinus, which are basically in the same places as your high pressure baroreceptors. Okay? The aortic arch and the carotid sinus are the regions where you have those baroreceptors. The aortic bodies and the carotid bodies reside in that same location, and they sense the gas changes. So you're going to have the same kind of communication that you had before. This is. There you go. So looking here, same general area. Your aortic bodies that are present at the aortic arch are going to communicate by which nerve? Which cranial nerve? Tendon, vagus. What about your carotid body, which is where your carotid sinus is? Glossopharyngeal, cranial nerve 9. Okay? Both of these are going to give you information about oxygen partial pressure. So this will tell you about hypoxemia. It will contribute maybe about 30% of the CO2 pH signal in circulating blood, but these are the only chemoreceptors that can sense directly changes in oxygen. Central chemoreceptors don't. This one's just kind of a close-up figure to show you relevant stuff from where we talked about before with our aortic arch, your baroreceptors on the left, and then you have your chemoreceptors here on the right, located in the same general location. The end result of this flow chart is what's going to happen in response to changes in your arterial PCO2. So if you had a shunt, for example, sometimes pulmonary shunt, that meant some of your blood from the right side is not getting oxygenated and was passing directly to the left side and mixing with systemic arterial blood, you end up with elevated PCO2. It's going to trigger both the central and the peripheral. As I said, peripheral is only about 30%, the central is responsible for about 70% of this response directly to CO2. The reason that we need to understand both of these is that while they both are going to contribute to the normal changes you might experience in pH just as a part of daily life, your peripheral ones can sense the partial pressure of oxygen even if there's no change in PCO2. So just the air you're breathing has a lower oxygen tension, which would happen if you went out to a higher altitude. The only difference is you lose that oxygen, but your CO2 hasn't changed. So your central wouldn't respond, but your peripheral would. All right. The microscopic anatomy of the carotid body. We're going to talk about this because the carotid body has been better studied than the aortic arch, the aortic bodies, but they have very similar structures. There are two types of cells that I want to mention. We have the type 1 glomus cell. That is your sensing cell. That's the one that's going to sense blood gas changes. The type 2 sustentacular cell is basically carotid body glia. Okay? Your glia are there to nourish and nurture and support the nerves. Your sustentacular cells are there to support the health and maintenance of your glomus cells. They don't do any kind of gas sensing. Your glomus cells are responsible for that. This is a simplified version. You'll see the complicated ones in the boron book in the next slide, which I included because, well, it's fantastically detailed, but it also has all the text to explain everything along with it. This gives you a relatively simplified way. There are many different mechanisms by which a drop in oxygen is going to be sensed by your peripheral chemoreceptors. All of them are going to result in changing the open-closure probability of your potassium channels. The result is if you close those potassium channels, less potassium can leave, so you end up depolarizing the cell. That will stimulate your calcium channels to open, voltage-gated calcium channels to open. And in any kind of sensory cell, elevated calcium triggers the fusion and the release of neurotransmitters from those vessels. Okay, so we do cover the specifics, all the nitty-gritty for that, that signaling sequence in 503. I don't expect you to start talking about synaptotagmin, synaptogrelin, all those things that we talk about in 503. That's 503 territory. For this class, you should know that the sensing of the oxygen results in the cell to be depolarized by closing potassium channels. So less potassium leaks out. That stimulates voltage-gated calcium channels to allow calcium to come in. And when that happens, you get neurotransmitter release onto the glossopharyngeal efferent. So this was the one I was telling you from the boron book. Really nice, very clear, and it walks you through all the different mechanisms. I mean, it is a very busy one, I understand that, but with all the text, I figured it does a pretty good job of explaining. But it does give you all of these different possible mechanisms here that show you how oxygen can be sensed. Okay? The drop in oxygen partial pressure sensed by the glomus, all of these are going to function to have a negative impact to shut down that potassium channel. You will have a moderate impact of a drop in pH or an elevation in CO2, also, which are going to have that negative impact here. So we have a drop in O2, an increase in CO2, and a drop in pH. All of these, hypoxia, hypercapnia, and acidosis, will all trigger closure of potassium channels. The result is elevated membrane voltage, more calcium coming in, and that gets more of your acetylcholine going onto your glossopharyngeal nerve. Okay? So those specific steps are the things that I expect you to know. The molecular sequence for how fusion occurs, not in the purview of 504. Okay? The CO2, you can see, will elevate and increase in protons because of your carbonic anhydrase, and your protons themselves will be able to enter in if you have that drop in pH. So all three signals, which typically go together, will all function under normal circumstances to trigger the exact same thing, which is closing those potassium channels. If you don't have the problem of elevated CO2 and therefore acidosis in response, because your activity hasn't changed, nothing has changed except you spontaneously went up to a very high altitude and now all of a sudden your oxygen tension is gone. Or, God forbid, you lost cabin pressure, okay? And you're elevated up there, you're sitting down, nothing's changed about your activity, so your CO2 is fine. You still have that change in PO2 for your peripheral chemoreceptors to be able to sense this change and trigger that signal to allow you to start breathing faster to bring in more oxygen. All right. This is something that I just mentioned before. I wanted to put up the equation just so that it was sort of a reminder from that figure that we had, or that short video where we had the soda water and the regular water, and it looked at the changes in pressure, right, and how you got solubility of the gas. It's the same principle here. This carbonic anhydrase is going to be very important when we get into the renal system. But carbonic anhydrase 1 is in your blood vessels, and you have carbonic anhydrase in just about every cell that you have. That is able to convert any of your excess carbon dioxide with water, produces carbonic acid, which immediately dissociates, giving you that proton and that bicarb. And that's how it impacts your overall pH change. So this is our feedback signal that shows that what is really going to happen if the main issue is you have a trigger up at the top. So you have an increase in your arterial partial pressure of carbon dioxide. What is that going to do? It's going to relatively weakly stimulate your peripheral chemoreceptors. The bulk of the work is going to happen over here. This is going to be about 70%. Ooh, that's terrible. Let's try that again. 70%. About 70% of your signal is from your central chemoreceptors that are going to sense that change in partial pressure of CO2 and the resulting drop in pH. It's going to do that because it has an abundance of that carbonic anhydrase to allow for the ECF, the extracellular fluid in your brain, is going to have a higher proton concentration as all that CO2 gets converted into protons and bicarb. It's going to stimulate those central chemoreceptors, both of which are going to function to stimulate that medullary respiratory center. The result is an increase in ventilation, and as you increase ventilation, you're blowing off more of that CO2, bringing in more of that oxygen, and as you blow off more CO2, the CO2 levels are going to drop, and it's going to relieve that full signal by dropping that arterial peak CO2. Okay? So this is your negative feedback, but this is how it's mostly going to be sensed. You'll have a weak stimulation from your peripheral if it's a CO2 mainly issue, which is typically the one that we have an issue with. But the bulk of it is going to be by changes in the pH in your extracellular fluid in the brain. This is the last one from this slide. I told you it was a short lecture. This is the last one from this slide. I believe this one is from the Guyton book or the Vernon-Levy, and it shows just exactly what is happening here. You have a cerebral capillary at the top, and you have your blood-brain barrier. That CSF is where your central chemoreceptor is located in the medulla. So as the CO2 diffuses across the blood-brain barrier, because it's a gas, it can mix and be converted into those protons and bicarb, and those central chemoreceptors right there at the pia mater are going to be able to send a signal into the medulla to elevate ventilation. Okay? On Thursday, we will do respiratory insufficiency, so restrictive and obstructive diseases, and then we'll finish up with high altitude